Hello everyone and welcome back to What the Heck Math. Today we're going to answer the question, what the heck are derivatives? Now derivatives is one of the most important parts of calculus. It's one of the first, other than limits, is one of the first major pieces of the calculus, or at least calculus 1 puzzle that you're going to learn about. And what it basically does is it opens up a whole nother area of math that you might not have thought was possible. I mean, I remember when I was younger, maybe what was it, middle school? Or no, I guess it had to have been elementary school. Yeah, definitely was elementary school. And my math teacher was telling me, we were taught that, whenever you do subtraction, you have to do the bigger number first. You can't do a small number minus a bigger number. You can't do that. It doesn't work. You can't do that. And so that's what I did, whenever I did subtraction, every subtraction problem I dealt with was big number minus small number. And then all of a sudden, one time, I was taught, actually, you can do small number minus bigger number, because then it would just give you a negative number. And I was kind of angry, because I felt like I was lied to by my math teacher before. It just kind of showed me that there was actually something that I thought was impossible that is possible. Well, it's very similar with derivatives. So I remember when I was taking algebra. So we're taking an algebra class, and we're learning about graphing and graphing equations and graphing lines, and then calculating slopes between lines. So if I have a point here and a point here, and I want to calculate the slope between those 2 points, well, it's very simple. You do change in y over change in x. So we have our change in x here, our delta x, and then our delta y, and you would just do delta y over delta x, and that gives you slope, m. And we were told that you have to have 2 points to calculate slope. You can't calculate a slope at a single point. Well, using algebra you can't, using calculus you can. And that's what derivatives allows you to do. It allows you to calculate the slope of a function at a single point. Now, if that function is a line, well, it's not very interesting to calculate the slope of just a line at a single point. So usually, I gotta make this bigger. This is too small. A little bigger. Okay. Usually whenever you're doing derivatives and you're calculating derivatives, you're doing it for functions that are not linear, like parabolas. So you can calculate the slope at that point. And so we talked about this earlier with the difference between instantaneous and average rate of change. So basically you're going to calculate the instantaneous rate of change, or the slope of the tangent line at that point. And that's what a derivative is. A derivative is slope of the tangent line. I remember when I took calculus in high school, every single time almost that we said the word derivative in class, my teacher made us then say slope of the tangent line. So derivative is slope of the tangent line. So it's a very important thing to remember when calculating derivatives. Now, real quick, hopefully this is this limit right here is familiar to you, because this is the limit that we've used to calculate instantaneous rate of change, and it is actually the limit that you would use to calculate derivatives. So for whatever function you're calculating the derivative of, you can use this limit to find the derivative of that function. Now, it does require you to do a little bit of simplification and canceling out, because you can't plug 0 in for h as it is, because you have to divide by 0. So you have to figure out a way to simplify that so that you then can plug 0 in, which then will give you a derivative. That's a lot of work. It does take some time to solve those limits, but there are some tricks, because there's some patterns that occur when you are solving these limits that once you recognize those patterns, makes it a lot easier to solve derivatives. So you might have one problem where you're solving its derivative using this limit. It would take you maybe 3 minutes of work, but once you find the shortcut, you can just figure it out in a second without even writing anything down, just in your head. The shortcuts are great. Okay. So before we get into those shortcuts, I'm going to go over a few things about derivatives, and if you see right up here, it's basically just notation about that you will see many times when you're dealing with derivatives. And it kind of depends on the teacher, the book, the website, or whatever, but they all essentially mean the same thing. Okay, so first of all, let's just start with one of the more common ones. I feel it's the easiest one to write. It's the easiest one to say, and basically, if you're dealing with the function, still red here. Let's go back to black. If we're dealing with the function like, I don't know, y equals x squared, and I want to say, hey, calculate the derivative of this function. One thing you can do is you can say calculate. That looked like a 1, but it really shouldn't be. Okay, calculate y prime. It's a tick mark. It's an apostrophe. Okay, so this is called y prime, and that just means find the derivative. That's all it means. It's a lot easier to say y prime. So this is a very common one to do. Now another one is now if this function was not y equals x squared but g equals x squared, then you would say, okay, find g prime. So just whatever the name of the function, this being the name of the function, is, put the apostrophe, then call it prime, so that would be your derivative. Another example would be dy over dx. Okay, now now the d is always going to be there, but the y and the x, that just depends on what variables you have in your function. So here we have y and x. So this can be read as dy dx. You don't have to say the over or the part. It's not really division. It kind of is, but we don't really treat it like division. Later on you kind of do with integrals, but it's not really division. So you call it, you can say dy dx, or you can say the derivative of y with respect to x. Okay, and it is important which one's on top and which one's on the bottom. Now if we had a function that was like I don't know, let's say a equals pi r squared. So here is a function for the area of a circle. So this function is in terms of r. So if you wanted to find the derivative of this function, it would be dA dr, because r is the independent variable and a is the dependent variable. Now I also have this one up here, ddx. Now this is you usually don't have this by itself. This is kind of more of a generic way of saying calculate the derivative. Usually if I want to say calculate the derivative of y or find the derivative of this, I would put the y out front. So you can have it in the top or you can have it over to the side. It also allows you to have something like, instead of y equals, what if it was f of x equals x squared? Then you can say ddx f of x. So it's to say calculate the derivative of f of x. So it's kind of like function notation. It's kind of like in trigonometry, sine of x and stuff like that. It's not d dx times f of x, it's d dx of f of x. You could also put, I kind of already said this already, but you can put the f up here because the function is called f after all, so you can put it up in the top. It also gives you the ability, if you have a function called f of x, just like we have y prime, we could say f prime of x. Okay, so these are all different ways that you can refer to a derivative, and you need to know all of them because you're going to be presented with all of them at some point or another. Like I said, f prime, y prime, that's usually the most common, but the dy dx is actually the one, to me, that illustrates the most of what a derivative is. And the reason that is because it's based on delta y delta x. Okay, so this is our slope function. This is our derivative. So dy delta y dx delta x. So the delta and the d are related to each other. The dy is basically means these are really tiny changes in y, and these are really tiny changes in x. So instantaneous change. So it kind of gives you an idea that these are actually related to each other. But again, you know, it's up to your teacher, it's up to your book, it's up to your worksheets, your test, or whatever, what they use. But all of these are really normally acceptable ways of referring to a derivative. Okay, now let's get to the cool part. Okay, so possibly by now you've been spending a lot of time solving derivatives using this limit, and it takes a lot of time. It's frustrating, but you notice that things always magically cancel out, and it works out great. And for people like me who love math, it's super exciting. For people like possibly you who don't like math, it's boring, it's tedious. Okay, well, let's get rid of that tediousness. All right, so let's actually start looking at these shortcuts. Okay, so the first one, okay, is if you have a function that is a constant equation, like y equals 2. Okay, now I'm going to generalize this to say y equals c. So c meaning constant, c for constant. Okay, so if you have any function that is just a number, and you're going to take the derivative of it. Okay, so I'm going to take the derivative of c. Well, let's think about what this means. Okay, so if I have a function like y equals 2, what does that function look like? Here's my x and y axis. And if I'm going to graph y equals 2, there's 2, and it's just going to go right through the middle. Now, what is the slope of this line? Well, the slope of this line is 0. Now, derivative is slope of the tangent line. So that means the derivative of c is 0. Okay, so that's the easiest one. So the derivative of any constant function that has no variable in it, it's just a number, is 0. And that, you know, it's the most easiest one to figure out. If you use the limit equation, it would have been kind of redundant to use the limit equation to solve that. So, but it is important though, because it will potentially help you solve more complex derivatives a lot quicker if you know that. Okay, so the derivative of every constant function is 2. Is 0. Sorry, backtracked. The derivative of a constant function is 0. Okay, now the next one, another very common one, is called the power rule. Okay, and so power rule is for functions like y equals x squared. So we have a function of x that has an exponent that is a number, not a variable. Okay, so we have an exponential function, or it's not really an exponential function, but we have a function where the base of the exponent of the exponential is the variable and the exponent is a number. Okay, it's very important to make sure you understand the difference between that. Okay, because there's a lot of mistakes that I see where people use this power rule for functions, for calculating the derivatives like that. Okay, these are different. The rules are different. Okay, did not apply. So the power rule does not apply for this one right here. And I didn't mean to do that. Okay. Alright, so let's try this again. Alright, power rule. Okay, so they apply for when the base is the variable and the exponent is a number, like x squared. Okay, so I'm going to generalize this, just like we did before. And the way I'm going to generalize it is we're going to look at y equals x to the n, where n is some number. Okay, yeah, so before I show you the rule, let's find the derivative of this using the limit. Okay, so let's just see what happens. Alright, so we're going to go limit as h goes to 0 so we're going to have f of x plus h, so that means x plus h squared, minus f of x, or just x squared, all over h. Okay, so now we got to figure this out, so that we're going to have x squared plus 2xh plus h squared minus x squared over h. X squareds cancel out, so then we have 2xh plus h squared, getting kind of tight here, over h. And remember, this is the limit as h goes to 0, so keep copying this down. Factor out an h from here, so we're going to have h, 2x plus h over h's cancel, and so let's go over here. So we're gonna have the limit as h goes to 0 of 2x plus h. So now we can plug in h, and then we get 2x. Okay, so what that means is if we have a function x squared, that means y prime is 2x. Okay, so let's see if we can figure out a way to, let's see what happened. Okay, well, one thing that happened is that our power of x decreased. So here our power of x was 2, and now our power of x is 1. Okay, so we can say, alright, well, y prime is going to be x to the, that's one thing that's going to happen. We're going to subtract 1 from our power of x. But also this 2 is here. Now where'd that 2 come from? Well, it came from right there. It just moved to the front. So we're also going to take that n and put it in the front. And here's your power rule. Okay, so for any single function that is x to the power of some number, this is how you calculate the derivative of it, right? So, I mean, if you want to say, okay, y equals x to the 1000. Now, if you wanted to calculate the derivative of this using the limit, it would take you a very long time. You would have to probably break out your Pascal's triangle, and it would still take you tons of paper because you gotta do x plus h to the power of 1000. Yeah. Or use the power rule. Okay, so we're going to take that 1000 and we're going to put it in the front, times x to the power of 1000 minus 1, or 999. And there it is. Very simple. And I can keep going. Okay, so for any power function, any function where it's x to the power of something, this is how you take the derivative. This is the power rule. You put the exponent in the front, and then you subtract 1 from the exponent. Very simple. Okay, now, here's another function, another rule that will help you a lot too. And again, it's very simple, but it's extremely useful. And that's called the constant multiple rule. Okay. Now this is for functions like y equals 2x, where we have a function of x multiplied by some number. Okay. And let's basically what you're gonna do here is this 2 can kind of come out. So for example, if I was gonna take the derivative of 2x, this 2, you can move it out to the front. So you can say this is equal to 2 times the derivative of x, of the function x. And it's just because it's multiplied into it, and it does use something called the product rule, which I'll show you in a bit. It's part of that. It's kind of like a simplified form of the product rule, or a special case form of the product rule, which is seen in a little bit. But it's very simple. So now basically all you do is gotta take the derivative of x. Now let's think, what is the derivative of x? Okay, well, let's look at it graphically. Here we have a function, the function x. That's not the function x. Okay, let's pretend like it crossed the origin. There we go, that's a little better. I'm really good at drawing straight lines, I don't know if you figure that out. Okay, so we have this function x, and we're going to take the derivative of it, which means we're going to calculate the slope of the tangent line. Now what's the slope of x? 1. So that means the derivative of x is 1. So that means if y is 2x, y prime is 2 times 1, or 2. And you can also calculate the derivative of x using the power rule, which we just learned, because let's just go to an x. What is the power of this function? Well, it's 1. Okay, so let's use the power rule. So we're going to move our exponent to the front, so 1 times x, and then subtract 1 from the exponent, so 1 minus 1, or 1 times x to the 0. What's x to the 0? 1. So you get 1. Okay, that's the constant multiple rule. So if you ever take a derivative of a function that's just multiplied by a number in the front, you can take that number out and then find the derivative of what is multiplied by. Okay, next one. Again, something that makes taking derivatives of like polynomials especially makes that a lot easier is the sum or difference rule. I'm not going to spell difference. Okay, sum or difference rule. So addition, subtraction. Okay, so essentially this is for equations like y equals x squared plus 2x plus 3. Okay, for taking derivatives of functions like this. Now again, all of these can actually be proven using the limit. Okay, so you could calculate the derivative of this using that limit and get the same exact answer that we're getting here. But it's a lot easier if you just use these rules. So the sum and difference rule basically says, let's generalize something. So we're going to say, okay, if we're going to take the derivative of a function like u plus v. So these are two functions of x. Okay, so you don't see the variable there, but they're two functions of x. Now it also works for u minus v, so we're going to call it u plus or minus v. And what you do is you just take the derivative of one, oops, and then you add or subtract, depending on which one you're doing, the derivative of the other one. Okay, yeah, so you just take the derivative of each function by itself. Okay, because they're just added or subtracted together. Okay, so let's see how that works for our example up here. So if we're going to take the derivative of this whole function, basically just if I want to find y prime, it's going to be the derivative of x squared plus the derivative of 2x plus the derivative of 3. This is the sum or difference rule. Now if it was subtraction, it would be the same. We just do subtraction instead of addition. So let's go through and do this. Alright, so y prime, derivative of x squared, well that's going to be the power rule. We didn't get the product rule yet. Power rule, so we're going to put the 2 in the front and subtract 1, so it'll be 2x plus derivative of 2x, well that's constant multiple rule. You can move the 2 into the front, and the derivative of x is 1, so it's just 2 plus the derivative of 3. Well, there's your constant function. So the derivative of a constant function is 0. So our answer is 2x plus 2. And again, if you solve this derivative using that limit, you would get the same answer. It would just take you a lot more time. Okay. Alright, product rule. Yeah, so this is the product rule and the quotient rule are as far as these that we're looking at now are the ones that are usually the most difficult, and a lot of mistakes are made in these, so you really want to be careful with these. Okay, now the sum and difference rule were basically the same thing. Addition, subtraction, they kind of go together, right? Product and quotient rule, they do look similar in some way, but they are very different, so I think it's helpful not to combine them like the sum and difference rule. Keep them separate because they're different enough, and you'll see what I mean in a minute. Okay, now the product rule. This is for equations where we have two functions of x that are multiplied by each other. So, for example, if I had a factored polynomial, like this, okay? Now you could just use FOIL and expand these and then just find the derivative of that polynomial just like we did on the last example, but it's also not necessary. Now that would probably be easier. Oh, excuse me, sorry about that. That would probably be easier, an easier derivative to find. But depending on how good you are at expanding polynomials, it might take you more time. But there are some functions where there's no way that you can write it any other way. You just have these two functions of x, you can't combine them, you can't use FOIL, Okay, so for example, if you had x squared times sine x. Now, we don't know what the derivative of trig functions are yet, but we'll get to that later at some other point, some other video. But in that case, there's nothing you could do about it. So let's pretend like we can't combine these, or let's pretend like we're not good at it, okay? So if I call this function u and this function v, the product rule states, okay, so we're going to take the derivative of two functions of x multiplied by each other. It's going to be equal to u, okay, now when I say u, I mean that function, the first function, unchanged, times the derivative of the second function, plus v, unchanged, times the derivative of the first. So another way that you can look at this that maybe is a little bit easier to remember and say is uv prime plus vu prime, or you can say v prime u plus u prime v. You know, it doesn't really matter which order you say them in, okay? So it's basically, product rule is one function times the derivative of the other plus the derivative of the, one function times the derivative of the other plus the other function times the derivative of the first. Okay, so you're gonna have to take two derivatives here, basically. So let's see how that would work with this one up here. So we're gonna find y prime, and so we're gonna just put u as it is. So 2x plus 2, and it's a good idea to put them in parentheses, times the derivative of v. And so it's going to be, we're going to use the sum rule. So the derivative of 3x, well, that's just 3. And the derivative of 6 is 0. So we're left with that. And we're going to add v. Okay, so that's 3x plus 6 times the derivative of the first. So that will be 2. And so let's simplify that. So let's distribute that 3. So we get 6x plus 6 plus 6x plus 12, and then we can combine, so we get 12x plus 18. So there's our derivative. Okay, now we could check this. We could just go ahead and expand this using FOIL and find the derivative of that polynomial, and we will get the same thing. Now I told you that the constant multiple rule is kind of a specialized version of the product rule. Let me show you why that is. Okay, so it's basically, it is just the product rule, but it's just a special case. So if I'm going to find, let's leave that there for now. I'm going to find, so let's go back to 2x. Okay, so it means u is 2 and v is x, so we're going to use this to find the derivative of that. So u, 2 times the derivative of v, derivative of x is 1, plus v times the derivative of u, what's the derivative of 2? 0. So you can say that this just simplifies to 2. Okay, so basically the constant multiple rule uses the fact that one of these two terms is 0, because the derivative of one of the two functions is 0, so it's kind of a special case of the product rule. Now the quotient rule, okay, in some ways it does look similar, but like I said, I think it's a good idea to kind of keep it separate because it does have a distinct, or a couple of distinct differences. Okay. Now the quotient rule, much like the product rule, is going to use two functions of x. So for example, we can have, I don't know, let's put something crazy. It's not crazy, but okay. Now I know this simplifies, okay? I know this simplifies to just x, but let's leave it like it is. But I think it's really cool to show how these things work with functions that we can take the derivative of in multiple ways, so we can see how they all give you the same answer at the end. Okay, so yes, this does equal just x, but let's just leave it like it is, and let's pretend like it can't. All right, just pretend. We're gonna start simple here. Okay, now the quotient rule uses, we use u and v a lot in these videos. So it's going to work the similar ways. We have two functions, u and v, and we're dividing. Now, it is important that you keep straight which one's on top, which one's on the bottom, and you match them up with our little equation over here to make sure you have them in the right order. The product rule didn't really matter that much. With the quotient rule, it definitely does. Okay. So what we're going to do here is we're going to take the bottom function and multiply by the derivative of the top, I'm sorry. So basically the first function you're going to take the derivative of is the numerator. The one is in the numerator. And you're going to subtract the numerator times the derivative of the denominator. So this actually looks very similar to the product rule. The main difference is it's subtraction instead of addition. Also, order is very important here. You have to make sure that your first term has a derivative of the numerator and your second term has a derivative of the denominator. Man, I'm just sneezing like crazy today. I'm sorry. Alright, so now all of that is going to be divided by the denominator squared. Okay. Now, you see why I say it's kind of similar to the product rule, but you don't want to connect them too much, because if you just say, oh, it's like sum and difference rule, product quotient rule, it'd be very tempting just to do the product rule and just change that to minus. But you can't forget about that v squared. Okay, so that's very important. Okay, so now let's see what happens if we take the derivative of this function using the quotient rule. Now, hopefully, if we do this right, taking the derivative of this will give us the same result as if we took the derivative of that. Now, what is the derivative of x? 1. Okay, so hopefully we should get 1 when we're done here. Now, it's going to require some simplification, but it's a good proof of this quotient rule to show that it does actually work. Okay, let's do this. All right. So first we're going to do v. So let's see, y prime. All right. So v is x cubed multiplied by the derivative of our numerator. Oops, I already messed up. Okay, I'm just jumping back and forth between so many things. All right, v is x squared times the derivative of u. U is the numerator, which is x cubed. So it's going to be 3x squared minus u, which is x cubed, times derivative of v, which is going to be 2x, all over v squared. So x squared squared is x to the 4th. And you might already see how this is going to simplify. So let's multiply that across. So we're going to get 3x to the 4th minus, so we got 6x to the 4th. Hold on, did I make a mistake here? No, I'm good. Okay. All over x to the 4th. Wait a minute. What happened here? Okay. Hold on. Let's try this again. Okay. Alright, let's try this again. Okay, sorry about that. Alright. V u prime. Okay. Or u prime v. I like to say u prime v. So u prime is 3. Uh-oh. How did that happen? Is that a good part? No, that's still too thick. Still too thick. Too thin. 2. So 3. Okay. Alright, u prime v. So u prime is 3x squared times v, which is x squared, minus v prime u 2x times, there we go. I don't know where that 6 came from. I made a mistake there. 2x, I'm lost. Oh, yeah, cubed. Okay, there we go. All right. And then v squared, which is going to be x to the 4th. Okay, that's better. All right. See, it's okay to make mistakes as long as you figure them out. All right, so now we're going to have 3x to the 4th minus 2x to the fourth all over x to the fourth, 3x to the fourth, 2x to the fourth, 1x to the fourth, x to the fourth over x to the fourth is 1. There we go. So you can see that it does work, okay, if you actually do it right. Okay. Now there's one more. It's a kind of an extension of the power rule, and it sometimes needs to be said because it's not inherently obvious, because it's for situations that don't look like it would still apply, but it technically does. And it's basically the power rule when the exponent of x is negative. Okay, so for example, y equals x to the minus 2. Okay, now the power rule still applies here. It applies exactly the same, because what we have here is a function of x, and its exponent is a number. Okay, if this was positive 2, you would do it. It would be 2x. Okay, power rule still applies here. Now you got to be careful though. Okay, because remember, let's write the power rule again. Okay, so the derivative of x to the n is equal to n times x to the n minus 1. So we're always going to put n in the front, the exponent in the front, and we're always going to subtract 1 from that exponent. So for this one, we're going to say, okay, y prime is equal to minus 2. So we put the whole thing times x, and then we're going to subtract 1 from minus 2. So what's minus 2 minus 1? It's minus 3. Okay, so the exponent will always decrease. Okay, so this is your derivative when the exponent is negative. Now this also works for when you're taking derivatives of like this, 1 over x. Okay, this can be rewritten as x to the minus 1. Now this, you can also use the quotient rule to take the derivative of that. Now I don't recommend it because it's going to take a lot longer than it would to take the derivative this way. But a lot of times, some functions, you can write them a different way to make it a little bit easier to take the derivative of. So it's a good idea to consider that when you're doing this. Okay. Now, one last thing, it's not a one of these rules or anything, but basically it's just talking about the fact that when you take derivatives, you can take derivatives forever and ever and ever. Okay. You can always take the derivative of a function. Now eventually that derivative might end up being 0, and the derivative of 0 is 0, and the derivative of that 0 is 0, but you can keep going. So for example, if I want to start off with this function, x cubed, I'm going to take the first derivative, which is going to be 3x squared. Now what if I want to take the derivative of that? Well, it's going to be called something else. I can't just call it y prime again. So usually what you'll call it is y double prime. Okay? And now I just take the derivative of that, which is going to be 6x. If I want to do it again, well, y triple prime. I want to do it again, y quadruple prime. And then I keep going, and this is 0 from here on out. Now there's another way you can write this, okay, so we can say, okay, y equals x cubed. I can say, well, the first derivative is dy dx. d equals 3x squared. The second derivative, now it's a little bit different, but basically what you do is you say d squared y over dx squared. Yeah, it's kind of weird that this 2's in the front and this 2's at the end. Okay, but I think it's basically because you can also put that outside, so it's kind of like the second derivative of y. And if you want to do the third derivative of y, we say d cubed y over dx cubed is 6, and the fourth derivative of y, that's a 4 dx to the fourth, and so on and so forth. So these are just derivatives are higher order derivatives. You can just keep going, keep going, keep going, and keep going. Alright, well that's about it for this lesson. Keep an eye out for another lesson about derivatives where I just kind of do a bunch of practice problems. This was mainly just to kind of show you how it all works, and then the next video I'll release, I'll show you we'll just go over some practice problems that use some of these rules by themselves. Some of the problems will use all of the rules in one equation pretty much. So thanks for watching. Please give me a comment if you want me to talk about something else. You got any suggestions? Subscribe if you want to get some notifications about when I come up with more of these. And I'll see you next time.